Thank you, Tom. Thank you for giving me the opportunity also today to talk to you and maybe a little bit more positive to celebrate how Sentinel-1 has helped us to advance forest monitoring over the past decade. First of all, a big shout out to the team in Wageningen and the many people I was able to work together with over the past 10, 15 years on this topic. And I also want to highlight that this presentation mainly presents results from our team and my own work, but there's many other groups that have contributed to this advancement on forest monitoring. But let's go a little bit back in time to the pre-Sentinel era, the time when I started my PhD in 2010. And I did a PhD on combining actually optical and radar data. And at that time, radar data was very limited. The access was limited, archives were fragmented, and was heavily underused. So I had access through the Kyoto and Carbon Initiative to a few stacks of ALOS pulsar L-band data. What was also true that the optical and radar communities worked very much in silos. So you had either groups that were solely focusing on radar data and other groups that were solely focusing on optical data. Monitoring was very dominated by Landsat data, and mainly annual monitoring, near real-time monitoring was lacking at the time. Radar pre-processing also required expert knowledge, and that in combination with very inefficient Earth observation workflows led to me during my PhD and many other PhDs and researchers of my generation that we spent a substantial amount of time just to creating an image stack that we then analyzed. But let me first take you to the South Pacific, where during my PhD I was lucky enough to spend quite some time. And working together with the Fiji Forestry Department, we also worked together with Fiji Pine, which is a commercial pine company. And they actually had data, very accurate data, and for me at that time was quite unique, on quarterly logging information on their pine plantations that they shared with me. And I considered that really my PhD lab outside the lab, because it was actually clear cutting, then trees were planted. And I was able to use that reference information to develop concepts for near real-time monitoring, to concepts to integrate optical and radar data on also how to assess the timeliness. And here's a first result with ALOS pulsar. There is something is not correct, but that's fine. With ALOS pulsar data and Landsat combining, so I was able to do that. And then there was 2014, the launch of Sentinel-1, and the big question was that to be our new workhorse for forest monitoring, in particular for the radar community, because for the first time it provided frequent observations with high spatial detail and data was free at a global level. But it was C-band radar. And C-band, because of a strong vulnerability to environmental effects and also the low sensitivity to forest structure changes, many people said, okay, C-band will not be useful at all for forest change monitoring. Also, Sentinel-1 is not a land monitoring mission. It's actually designed to monitor maritime regions, and that's its main purpose. So the focus of the early years was really to find out to what extent we can reliably use Sentinel-1 for forest monitoring. And here we see an early image in Bolivia, where we actually can see quite good contrast between forest, the bright areas, and then the clear-cut areas. But if we go like the next observation, 12 days later, we actually see that this contrast diminishes immediately. And that is because just of increased soil moisture. After a rainfall event, soil moisture increase makes the backscatter the radar signal to jump up, and that diminishes the contrast in C-band. And that was also the reason why in the past, where we only had very few images, C-band radar wasn't very useful for change monitoring because we didn't have many images available. But now, thanks to these dense observations, we were able to compensate for these environmental effects. And what we see here, the fluctuations in the time series, is actually the effects of sudden soil moisture differences in the signal. But because we have this dense information, we can actually also reliably see changes in forest. And here an earlier result also of a local study where we used then Sentinel-1 data for more timely monitoring of forest loss, where we see that it improved the timeliness compared to Landsat data, and when we combine it, it's even much better. And then the years following, we really worked on scaling up these methods to the pantropics, to continental scale, and that was supported by two key developments. First of all, really investments in analysis-ready radar data. At that time, we had access to analysis-ready optical data, and that's why it was used also at such an extent, but it still required additional pre-processing to use radar data. So what we did, for example, in Earth Engine, there was Sentinel-1 data, but we still needed additional pre-processing to do that. And we also released an open package that is now cited more than 350 times that allows users to produce analysis-ready radar data in the Earth Engine. But in parallel, there was other initiatives like the CEOS ARD group that actually very clearly defined what is analysis-ready radar data, and those standards are now used to also by space agency to produce that more operationally. This is a great development because it allows users to directly tap into these radar data sets. And the second thing, of course, is the availability of cloud computing and analysis platforms that allow us, that host these satellite archives and that allow us to analyze this new satellite data at a global scale immediately in near real time. And there is Google Earth Engine, but now very luckily also the European solutions that are developing rapidly. And those developments and collaboration with Global Forest Watch allowed us to actually operationalize those concepts that I developed during my PhD in Fiji to the pantropical scale, into the RAD alerts, which now already since 3 years provide weekly updates operationally on new forest disturbance across the pantropics. They're openly distributed. And what we see here, I mean, I like to show this animation because it really demonstrates the high spatial and temporal detail at which we are now, at that time, for the first time, actually were able to track forest disturbances. Is what you see is a logging road being established, and then shortly after the road is being established, you see in the direct surroundings the indication of selective tree extraction. And that's something, a detail we weren't able to see before. And at that time, that was actually the first large-scale Sentinel-1 based land application that existed. It's really a law enforcement and transparency tool. So it's really there to support forest users in tropical countries to have an early indication of activities, and then if there's a potential unsustainable or illegal activities, to follow up and try to intervene. And those radar data, those radar alerts, they are very complementary also with optical alerts. And we work together with University of Maryland on an integrator alert that integrates the optical alert produced by their group and our alert into now an integrated alert tool. And that data really allowed us to look into processes at a level and uninterrupted that we will not be able to do that before. And here we see, for example, smallholder agriculture expansion in DRC, where we clearly see these small patches of forest that are cut at the edges of big remaining forest patches, and after 2-3 years the soil is exhausted and a new piece of forest is cut, and that process slowly eats itself into these large unfragmented patches. So what we did after that is to focus on to provide more context, because after talking to users, we very much heard how important it is to not just know where and when something happened, to also understand what drove these changes. And knowing that information, not retrospectively, but in near real time, is very important. So we very much focused on also labeling the type of change we are dealing with. And this is work that has started a few years ago, but we were now able to actually scale that to the pantropics to do this near real time. This is work in review now, so we hope to soon release a data set that at least on a monthly level provides a direct driver of loss in addition to the timing. And here is some examples, some early examples where we clearly see like smallholder agriculture next to mining, for example. But here's also an example from the current data set in Borneo that shows on the right side, you see a lot of mining, you see logging roads, you see selective tree extraction, you see large-scale agriculture, you see small-scale agriculture. It's a very complex interplay between, in particular, the small-scale drivers that, because we do it spatially explicit, we can basically now try to understand the complexity of these drivers, something that isn't able if you do it at a spatial aggregate level, how many data sets that are currently available, they do it in aggregated at a 1 or 10 kilometer level, and there we lose that detail of particular small scale drivers. What we also see, because we have this data now at least monthly, we can look at the temporal patterns of these drivers, and on the left side we see an area dominated by agriculture and mining, and we see basically that in 2022 we did see a lot of mining and then it slowed down, but what we see is this seasonally reoccurring patterns of agriculture that is very typical, where smallholders in the dry season, that's when forest is cut, and for the rest of the year nothing happens, and then next year there's another patch cut during the dry season. But what we also see is, for example, on the right side, is that logging road and logging activity started in the first years, and then suddenly in 2024 we've seen a fire in an area where we've seen previously human activities, and probably because of opening of this area, that area got vulnerable to a wildfire or a human started fire, and then it's very likely an escaped fire. And then there was December 2021 when Sentinel-1B actually died, and those are the shoes of one of our PhD students. I'd say that is real dedication. You have these Nike shoes that you can customize, and that's how he customized them himself. And Sietze, actually, he's also responsible for moving these methods that we developed in the tropics to the European context, and we now adapted those alerting methods to Europe, and we now have a European red alert that we hopefully will release operationally by the end of the year, weekly updates on forest disturbances in Europe. And that's quite exciting because we can combine now these weekly information with agent information together with Corneo-SEM through a different EU project, and we can actually look at disturbance agent seasonality in Europe, really decode what drives disturbances and different disturbance types. And what we see here is, for example, in Finland, very typical north of Finland, we have these winter logging activities when the soil is frozen, and a little bit in spring. In the United Kingdom, we see the effect in spring. We see they have a lot of spring logging, and what we see actually is wind and bark beetle is not, there's some wind events, but for bark beetle, it's often what we see is salvage logging as a result of bark beetle and the fire increase. And we're now studying to find out what drives these differences across Europe. How much is management related? Because, for example, Finland does winter logging very much, and the UK does spring logging. And what is climate driven? So that's very exciting. And the last part of this presentation, I want to focus on work we're doing on tracking logging impact. So if we process the Sentinel-1 data, well, we can very clearly see the indication of not just logging roads and some canopy openings, but almost all canopy openings, because what we eventually see here is three-dimensional gaps in the forest canopy that appear, where we have this dark area, which we call on one side is radar shadow, that is not seen because it's a side-looking geometry radar sensors, and on the other side we have foreshortening and layover, we see these very bright signals. So it's a very clear indication of three-dimensional loss of forest canopy that we can observe very, very clearly. But why do we want to? Also, I skipped that slide. So tracking selective logging is very, very important, because illegal logging activities globally is about 15 to 30%. In some countries, it's up to 90% illegal activities. But selective logging is not just illegal. If done sustainably, it's one of the best ways to actually respond to the demand for tropical timber. So we shouldn't always see it as, something bad. It's also a good thing, selective logging. And if we see, for example, in FSC concessions, they are very well managed. And those areas, the wildlife is often more protected than in other areas, because those FSC concessions, they make sure that there is no poaching activities in the areas, for example. So what we did, so Bart led work on actually now mapping on a monthly level very accurately the logging roads across the Congo Basin using Sentinel-1 and Sentinel-2 and deep learning. And then another example is from Yule, and for her work, we were interested in really improving the estimation of timber harvest volume. So going from just the detection of area to timber harvest volume, and what we, in the first step, what we had available is actually reliable drone-based reference data on felling gaps for a number of concessions, and that allowed us to develop an improved Sentinel-1 based detection method that is now published, that very much focus on improved detection in logging concessions, and that combined with in situ information from the Nature Conservancy, large scale across the Congo Basin and other tropical regions on harvest volumes, allow that now to some extent estimate harvest volumes from Sentinel-1. And here's an example that shows that this allows us now with about 20% uncertainty to track the development of logging through different compartments, subcompartments, forest management unit within larger concessions. And we can also aggregate it across the Congo Basin. Let me conclude. So first of all, I would like to thank you as being a radar scientist. Thank you, Sentinel-1, for making radar sexy again, because it was considered very unattractive when I started my PhD. Everyone started to worked with optical data, and I think now, including Tom, many people pick up radar data and recognize its use. The high spatial and temporal detail really helped to overcome the limitations of C-band. And we were able to shift from monitoring to near real-time alerting and even impact assessment. So for example, the impact of selective logging. And the open access and the global coverage, as many data sets we've seen today, really led to widespread uptake. And it really helped to expose the spatial temporal complexity of fine-scale disturbances and human activities. But we do that, the most important part of the work we are doing is really to provide information to empower forest users and protectors around the world. And those are the real champions, because they risk their life to protect their forests. And without them, our work would not be very useful. And I actually had a discussion with Christoph yesterday, and we talked about, we had this, what Tom brought this up, this policy relevant data, going from analysis-ready data to policy-relevant data. But what is actually important for those? Policy-relevant data might be important for policymakers in Europe to track implementation of policies, but what they actually need goes a step further. It's evidence or forensic-ready data that can stand in court, because that's what they need. They need data after arresting someone that illegally logs forest. And there is remote sensing evidence that started that, for example, that data needs to hold in court, and that comes with many other requirements for ownership, for example. A very good example is Mapiomas, that produces these automatic reports with a pre and post change image, and that goes into this direction of evidence-ready data. That really goes a step further than policy-relevant data. It's something I'd like to think about more, but good discussion. So it wasn't just my idea, it came through a joint discussion. And future directions, I foresee many more Sentinel-1 based forest applications with improved contextual detail. And now the availability for the first time of multi-frequency radar data. So we for a very long time worked with C-band data, which saturated very quickly if it comes to forest structure. We now, for the first time, NISA was launched in July. The first time we will have access to, in a similar manner, frequent high-resolution L-band data. L-band radar data, it's a longer radar wavelength. It's much more sensitive to differences in forest structure. And also P-band, which is not from the biomass mission, which is not a monitoring mission, but it still provides information on forest structure. And those in combination will allow us to much better understand forest structure and forest structure changes. And with this, I would like to conclude and thank you. And here is actually an image from last week where Sentinel-1D, so the fourth Sentinel-1 satellite, has arrived in French Guiana and is being prepared for its launch. Thank you very much.
Thank you, Johannes. Let's see if we have questions. Here, one second row.
Thanks for the very nice presentation, Johannes, and also the discussion yesterday. So to continue that discussion, do you get feedback from your forest end users when they are able to use your alert system to actually stop the crimes from happening? Do you get feedback on that? And can you then do analysis on that to see where they were able to use it and when they're not able to use it?
So that is very different. We work also together with countries a lot and we gather this feedback. But as I said, in a lot of countries, it is the case that those information we're having is for transparency. It supports them, but it's often that it's in-country data that is required to basically to be evidence of forensic ready, because it needs to be generated by an organization in the country that actually has the mandate to generate that data. So it's very complex. We get this feedback, we have a lot of discussion, but this whole legal workflow, this is often where it lacks, where really the impact lacks. I mean, the data is there, we don't need more data, but what we need is actually legislation in those countries that allow to use this data actually to prosecute people. And we hear a lot of stories, we talk to people that are very frustrated in their countries because the data is there, but it's very hard to actually follow up on these data that shows obviously unsustainable activities. It's not so easy.
Greg, yes.
Hi, Johannes. Thanks. Very nice talk. I was wondering also if you could tell us a bit. I mean, you showed a lot of examples, quite localized, because to see the roads, to see the patches and things like that. And I know SAR is quite effective at going through the clouds everywhere, but you also showed us how with the soil the humidity or whatever, I mean, it actually affects your signal, no? And so I was wondering a bit if you could tell us a bit, or if you have a bit of a feeling also on if it's working as well as it seems everywhere. Can we trust this as something that is like stable features across the domain, because that we can trust it as effectively everywhere? As when you show me one that I see that it's like getting disaggregated and you see advancing the forest lines for sure. But then I wonder, can I use this blindly everywhere thinking, okay, I can treat everything without context? I mean, you see what I mean?
Yeah. I mean,
where are we at in this level?
Yeah. So the point is so we have omission, obviously. So also in the examples I showed, you see roads that are not connected in these individual examples, but what we actually detect, and that many showed, there's a very, very low commission error, but that's also how these methods are designed, alert methods. So I would say, so whenever we actually detect a change, we are very confident that the change is true, but we also omit quite some changes.
Okay.
And that level of omission, that ranges. And that's why the integration with optical data is very important, because, for example, with C-band, they're very good because what I showed, we have this signal of radar shadow and foreshortening to see this small three-dimensional loss of canopy. But what we are very poor at is, for example, seeing fire changes where a lot of structure remains. We see huge emissions and delays, but this is where optical data does very well. So we have quite a good understanding in which types of changes we can reliably map and which we can map less. So it's not depending on the region, it's more depending on the type of change and the magnitude of change we're dealing with. But what I want to say is that leads to omission, not necessarily to commission. Mm-hmm. I think this is one of the advantage of this, is that it has a very low, improvement also by others, a very low commission rate. But the omission rate varies depending on what we are looking at. Thanks. I'm not sure if this answers your question.
Later. There's one more question, Stefan.
But the driver data is actually integrate alerts that has not just the radar data that is underneath that we disaggregate, but also the optical data. So it's both combined. So.
Okay, thanks. Now I have one more question, which is actually related. So it's really interesting when I talk to people. Some are really convinced that radar is adding lots of value. I was talking to a Polish guy, I can't remember exactly where he was from, I think statistical office in Poland. He said they mostly now use for even crop specific applications, crop type mapping, more radar than optical. And then I see a complete opposite. So I was talking to one company, GeoVille, and they are doing mowing events in Europe for Copernicus services, and they are not using radar at all. And I asked them why are not using it, and they said they did some tests and it added no value. But I personally don't believe it, but it's not so easy. So my question is, maybe they are not yet fully familiar with all the ways to interpret it properly, to use it correctly. So I think there's still a lot of work which needs to be done to integrate radar fully, and it probably will depend on how you use it, and you need to be a technical expert. I think that might be the reason.
That's true. We see that a lot. That, I mean, thanks to analysis ready data, many people can use it, but they use it inaccurately, and then they draw conclusions that might not be correct, because often the radar interacts with objects on the ground and with changes very differently than the optical signal. And sometimes these signals can also cancel out each other. So if you put them just in one model inaccurately, you will see that there is no benefit, because I've seen a lot of students that, for example, do internship at companies also wanted to look at mowing, and then they did it very inaccurately, for example. But we've seen it for rice monitoring, for agricultural monitoring. C-band is very useful because it's sensitive to these smaller objects, and agricultural, crops, they try to start growing very slow and not at so radar, this is 5 centimeter wavelength, so it interacts with objects that have roughly the size of the wavelengths, 5 centimeter. And that's why it's very useful for agricultural monitoring. If you understand all the other processes, how soil interacts with the signal and so on, I think it's a lot of education that still needs to be done. But it's not, it also has its strong limitations, of course, but.
And just one more thing before the coffee break.
But I think there was also you. Okay, sorry.
I just wanted to, if I may, jump in. We had in this project, when we wrote the proposal, it was Stefan, Fritz, Martin, Harold, me, and Leandro. We started the proposal. So we had this idea to have this fusion in situ and Earth observation. And one of the things we got very excited is this sensor system they developed in Bolzano, I think, called Tree Talker. I don't see in your presentation, do you foresee, like in Europe, we could have eventually, if we get a project, let's say that we have these tree talkers, sensors, so like a stations on the trees, and then measuring physiology of trees and the health of the trees, and then combining that data directly with the Earth observation data. And how many stations will be needed to have a European?
Yeah, that goes way. I wouldn't know. That's maybe better to ask the people in Potsdam. But just what I want to say, like C-band, if we look at forest parameters, the sensitivity is very low, because the signal saturates over forest very quickly. What we see is abrupt changes in forest. We see a gap in the canopy. That's what we can detect very well. But what we're not able to do is like subtle differences in forest structure parameter. It's very insensitive C-band to that. It's sensitive to small changes if you have bare soil and then the crop grows, because that is sensitive. The wavelengths are sensitive to it. But those interactions are very different. Again, what it relates to what Stefan said, very different to optical data. And I think you still need some proper radar expertise to use this data. Well, that's not answering your question, but but it relates a little bit, because then I say people, okay, we can use it well to monitor rice, for example, operationally. Why it's so insensitive to, for example, basal area? Because you say radar is sensitive to structure. Yes, C-band radar is sensitive to structure related to the 5 centimeter wavelength, but not to forest objects that are much bigger.